We're going to review exponential functions in this video. And first we're going to start off with simplifying expressions using properties of exponents. So we're going to just do a reminder of what some of our exponential properties are. If I have 2 squared times 2 cubed, and I want to simplify that, another one would be 2 squared times 2 to the negative 3. And then another one would be 3 squared raised to the 3rd power. So we'll start with those three first. If I have 2 squared times 2 cubed, that's the same thing as 2 times 2, which is your 2 squared, times 2 cubed, which gives us 2 to the 5th power. Notice how the base stays the same, we add the exponents. So that's one property that you might recall. So when we add the exponents here, the base stays the same and we get a negative 1 power. We're going to make that negative exponent positive by bringing the base and the exponent to the denominator, making the exponent positive, which simplifies to be 1/2. And then in this next one, we have a base of 3 raised to the 2nd power, raised to the 3rd power. That's when we multiply. So 2 times 3, power to a power, we multiply. That would be 3 to the 6th power. And 3 to the 6th power is the same thing as 9 cubed, which is an exponent on our exponential facts. That would be 729. Okay, let's do 3 more. So we're going to have 1/3 raised to the negative 2 power. We'll have 3 squared over 3 cubed. And then we'll have 2 to the 1/2 times 3 to the 1/2. So we'll start with D. 1/3 raised to the negative 2 power is the same thing as 3 over 1 raised to the 2nd power. And that would be 9. 3 squared over 3 cubed is the same thing as 3 times 3 over 3 times 3 times 3. That's going to leave us a 1 in the numerator and a 3 to the 1st power in the denominator. So here you can retain the base of 3 and subtract the exponents and get 1/3. This one's a little tricky. These two have the same index, so I can rewrite this as the square root of 2 to the 1st times the square root of 3 to the 1st. So I'm going to take those rational exponents and I'm going to rewrite as a radical. So the base is the radicand, and then the 1/2 power, pay very close attention here. Here's your 1. 1 goes right here, and then the denominator is the index. So that's how I got the square root of 2 times the square root of 3. And the square root of 2 times the square root of 3 is the square root of 6. So that would be 6 to the 1/2 power. Now another thing that we can do is we can say, well, we can regroup this and say 2 to the 1/2 times 3 to the 1/2 is the same thing as 2 times 3, both raised to the 1/2 power. So it's using that product property from exponents and going backwards. And then that would give you 6 to the 1/2 power. So that's kind of a little nifty property to recall. Something else you might recall is when we're working with exponential functions, we have y equals a times b to the x power. In fact, this is a concept that I am making videos on for my Algebra 1 class. So don't be alarmed that, oh, that was in Algebra 1. We are reviewing it for a reason, because when you don't use it, sometimes it's not easily accessible. You lose some of the information. So let's do this problem. In living organic material, the ratio of radioactive carbon isotopes to the total number of carbon atoms is about 1 to 10 to the 12th power. So a ratio is a fraction, and the ratio of isotopes, the ratio of isotopes to the total number of carbon atoms, so isotopes to atoms, is 1 to 10 to the 12th. Not sure where we're going to use that, but that's this information right here. When organic material dies, its radioactive carbon isotopes begin to decay with a half-life of about 5,715 years. That means that if I start with 10 grams, then in 5,715 years, I will have 5 grams. So I will lose half of what I started with every 5,715 years. It's important for you to know, every 5,715 years, we lose half. So they're going to explain that. This means that after 5,715 years, the ratio of isotopes to atoms will have decreased to 1/2 the original ratio. After a second 5,715 years, the ratio will have decreased to 1/4. So our half-life means that our base, this base right here, is going to be 1/2. Figure 4.1, we don't have a figure 4.1. It shows the decreasing ratio. So I'm showing you right here in our equation, and I'm explaining it to you. So here's our formula. This is what we're starting with. We're starting with 1 over 10 to the 12th power. So that's our initial value. So initial value. And this is our, let's make this a different color. This right here is our decay factor, which is 1/2. And then we have T. T is equal to the number of years, because we're talking about 5,715 years, since the organic material has died. And R, our output, stands for the ratio of isotopes to atoms. So our beginning ratio is 1 over 10 to the 12th. Every 5,715 years, that ratio is going to get cut in half. So if I have 10,000, actually it would be 11,430 years, that would have decayed twice. So every 5,715 years, we decay. But you can see here, 10,000 years, we don't know how many cycles that's gone through. It's gone through 1 full half-life, but it has almost a second one, but not quite a second one. So this is how we calculate the R value, which is your ratio of carbon isotopes to carbon atoms. So R is equal to 1 over 10 to the 12th times 1/2 raised to the 10,000 over 5,715 years. Now that's not quite 2 half-lives, but it's almost. We're going to put this into our calculator. I'm going to call this A right here. We're going to put this into our calculator, and we're going to get a value that's in scientific notation 2.973 times 10 to the negative 13 power. So take a look at your calculator and make sure that you can read that properly in your calculator. If you did not get that, you're putting in parentheses 1 divided by 10, upper caret 12, end parentheses, 1 divided by 2, end parentheses, upper caret, parentheses, 10,000 divided by 5715, end parentheses. That's how you would enter this into your calculator if you have a basic calculator. If you have a fancy calculator that shows you the fractions, you can enter it exactly the way you see it. But for most of us that don't have those fancy calculators, this is going to be really important for you to know how to enter into your calculator. For B, we're going to do the same thing, except this time we're going to put a 20,000 in our numerator in our exponent. So 20,000 over 5,715. And when we put that into our calculator, I would press pause, or you can keep going, and if you're ahead of me, then you've got 8.842 times 10 to the negative 14. And C, I would most definitely try this one on my own. We have R equals 1 over 10 to the 12th times 1 over 2 raised to the 25,000 over 5,715 power. Putting that into my calculator, it's approximately 4.821 times 10 to the negative 14. Now we can rewrite each one of these. 2.973 times 10 to the negative 13 is 2.973 over 10 to the 13th. And this would be 8.842 over 10 to the positive 14. And this would be 4.821 over 10 to the 14th power. So that would be the value of R as a ratio. Let's talk about graphing. We're going to graph each exponential function. We're going to start with a parent function that's very common, f of x equals 2 to the x power. Now I'm going to talk about putting values in and out. So hopefully you know your rules of negative exponents and you know your exponential facts. 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, and so on. If I were to put a negative 10 in, I would have 1 over 1024. 1 over 1024. That is a very small number, very, very close to 0, but not quite 0. If I put a negative 9 in, I would have 1 over 512, still a very, very small number, close to 0. If I put an 8 in, I would have 1 over 256, and so on and so forth. So these numbers are very, very close to 0. If I put a negative 3 in, I have 1 over 8. If I put a negative 2 in, 1 over 4. If I put a negative 1 in, 1/2. If I put a 0 in, 2 to the 0 power is 1. If I put a 1 in, I get a 2 out. If I put a 2 in, I get a 4 out. And if I put a 3 in, I get an 8 out. The graph f of x equals 2 to the x power is an exponential graph that on the left has a horizontal asymptote. This has a horizontal asymptote at y equals 0, meaning that function value is never going to equal 0, but it's going to get very, very close. Now the accuracy when we're drawing these is very important. So I'm looking for specific lattice points. Let's look at the next one. f of x equals 1/2 raised to the x power. Well, this time if I put a negative 10 in, I'm going to get 2 to the 10th power, which is 1024. If I put a negative 9 in, I'm going to get 2 to the 9th power, which is 512. So the first value that I can put in from the left-hand side is a negative 3. When I put negative 3 in, I get a positive 8 out. Now I could put in other values, but for this grid, that's the first value I can put in and get out on this grid. If I put a negative 2 in, I get a 4 out. If I put a negative 1 in, I get a 2 out. If I put a 0 in, I get a 1. If I put a 1 in, we get 1/2. If I put 2 in, 1/4. 3 in, 1/8, and so on and so forth. This exponential graph actually models decay. It too has a horizontal asymptote at y equals 0, but this time that horizontal asymptote, which is at y equals 0, is only in effect, it's only applicable as x gets large going towards positive infinity. I had to think about a word that I was wanting there. I still didn't get the word that I was wanting, but okay, here's h of x equals 3 to the x. Let's see if you can come up with this graph right here. Okay, when I put a negative 2 in, I get a 1/9. When I put negative 1 in, I get 1/3. When I put a 0 in, I get a 1. 1, 3, 2, 9. This graph models exponential growth from left to right, and it has a horizontal asymptote as x approaches negative infinity. It has a horizontal asymptote at y equals 0. It has a domain. All of these have a domain of negative infinity to positive infinity. So let's write that. Domain, negative infinity to positive infinity, negative infinity to positive infinity, and negative infinity to positive infinity. The range for each one of these is 0 to infinity, not including 0, so it's an open interval, 0 to infinity, and 0 to infinity. Those are all the outputs. All three of them have a horizontal asymptote at y equals 0. We know that horizontal asymptotes are another way to say the limit. So the limit as x approaches negative infinity, we're talking about a right here. This one is a. Then we'll have b, and then we'll have c. When we're looking at the graph for a, the limit as x approaches negative infinity of 2 to the x power is equal to 0. And that's because as x gets really, really large negatively, our function value is getting closer and closer to 0. And for graph b, the limit as x approaches positive infinity of 1/2 raised to the x power is equal to, that is also equal to 0. And then c, how do we write that horizontal asymptote as a limit? That limit as x approaches negative infinity of 3 to the x is equal to 0. And those are our exponential functions that have horizontal asymptotes that can be written as a limit as x approaches positive or negative infinity.